Good evening all. Welcome to the live session for NPTEL course on fundamentals of convective heat transfer. This is week 5. This week we will be discussing on the topics of hydrodynamic and thermal regions, and then we will discuss something called fully developed flow, and we will take the energy equation for a fully developed channel flow, and we will come up with equations for the overall heat transfer and the heat transfer coefficient. We will not be solving the equations in this session, but we'll provide some of the important definitions that will be useful when we derive the solution in the next week. In this week, we will solve the hydrodynamic one, where the velocity profile is solved. And in the next week, we will solve the energy equation and come up with an equation for the temperature as well. So the key difference between the flows that we were discussing in the last week and in this week is the last week we were discussing on external flows where we have the boundary layer. In different cases, we have tread with constant wall temperature, uniform heat flux, and without any like the ambient as well as the wall temperature is same. That is only the hydrodynamic boundary layer. And then we discussed when the wall temperature is different from the ambient temperature, then you have a thermal boundary layer. But in all of them are classes where you have external flows, where one side is wall bounded and the other side is open to. But here we discuss something called internal flows, where you have wall boundedness on all the sides, so that flow is something like, as example is a flow in a duct or in a pipes, where you have something like this, and then some flow is happening inside this one. So these are the kind of flows that we will be discussing in this week. The flow will be happening here. These are internal flows, so both of these are walls. Now the Reynolds number here, but is for in the previous case when we were discussing on boundary layer, the non-dimensional number that we were using is again the Reynolds number. But then the Reynolds number was defined on something called the free stream velocity. But the free stream velocity is something that is imposed by the surrounding conditions. Here what we are imposing is some depending on the type of problem. Here both sides the wall is there, and we are not imposing the velocity directly. So the velocity here is something called the mean velocity. We will take the mean velocity across any given cross section, the average velocity across a given cross section, and we will use that velocity scaling, that um as my velocity scale. The remaining quantities are the same. These are the fluid density and dynamic viscosity, and D is something called hydraulic diameter, which we will discuss in a little while. Depending on the type of geometry that you are going to have, the value of D will keep changing. If these are two plates, parallel plates, you have one kind of value here. If it is a circular pipe or an annular pipe, you have a different value of D. So that is something called a hydraulic diameter. So the length scale here will depend on the geometry as well as the type of flow you're going to have. And the most important thing for all of these problems, even in the previous case when we were discussing for flat plate, is all of the discussions that we are doing now are restricted to the laminar flow. So when you are applying any of these derivations or any of the concepts that we are discussing now, you have to first check whether that particular flow is laminar or turbulent. So the criteria here is the Reynolds number with the characteristics velocity and the corresponding dimension and scale should be less than 2300. This is for pipes or ducts. So what was the value in case of external flows? Yeah, for external flow, we require Reynolds number to be less than. This is for laminar condition. And another important distinguishing factor between the external and internal flows is the way that we define this Reynolds number in an external flow is as you go along the plate. So if you have an external flow, and if you move along the plate, so this is my x direction. If I move along the plate, the Reynolds number keeps increasing. So we define the local Reynolds number, which is keeps increasing as x is increasing. So if you consider 2 points 1 and 2, both these points will have different Reynolds number and corresponding with the boundary layer thickness, the local shear stress, and all those factors will change, which we discussed up until last week. But in internal flows, we are defining Reynolds number in this way, where this dimension, the characteristic length scale, is constant throughout the depth. Like it's constant throughout the flow. So this Reynolds number is a constant number. So why is this fact important? Like, wow, what do we make out of this? Yeah. So whenever we put a criteria like this, Reynolds number less than 2300 or Reynolds number less than 5 to 10 power 5, in external flow, this Reynolds number keeps increasing as x increases, which means there exists a transition point in external flows. Here we will have a transition point. To the left of it, we'll have a laminar region, and to the right of it, we'll have a turbulent region. That is the main thing that we have in an external flows. But in internal flows, the Reynolds number is fixed from the beginning itself. So if it is laminar at the beginning, then it will be laminar throughout. If it is turbulent at the beginning, it will be turbulent throughout. That is the most important thing that you need to keep in mind is for internal flows. And why is that so? So what is causing the thing to become turbulent here, and what is that particular thing that prevents it, and or what is that particular thing that maintains that flow to be still laminar if it is laminar in the inlet is something that you will understand much later once the turbulence is introduced. But for now, this is the important fact. At least the way we are providing, the way we are non-dimensionalizing the governing equations, or the way we are studying the system defines in this way that Reynolds number is such that if it is if at the inlet it laminar, then the same Reynolds number is maintained throughout the duct because the D is same. Yeah, now obviously this is assuming that your the mean velocity is also constant, which we will discuss in certain in next slide, where you introduce the concept of a fully developed flow. A fully developed flow is one where your velocity will not keep changing beyond a particular point. So everywhere you'll have the same kind of cross section. So this velocity profile will be here. At any x you take, the velocity profile will remain the same. So in that particular case, the mean velocity, if you were calculating at any cross section, it will be same. And this d is also a constant if you have a uniform cross section. So if you have a uniform cross section duct with then under fully developed conditions where u, m, and d are constant, under those scenarios, this Reynolds number will be constant and this particular thing holds. Okay. Now this is for the hydrodynamic part. Next comes the thermal component. So again, for a thermal energy to be transferred, there should be some temperature difference. Again, we have two different boundary conditions. We can have either a uniform wall temperature or you can have a uniform wall heat flux. So what are the scenarios when you have uniform wall temperature? Like why do we have these two different boundary conditions? Why not anything in between? Yeah, of course, we can have anything in between, but like, these are the kind of extreme cases. So for example, if you have a fluid flowing through some pipe, and the material of the pipe is highly thermally conductive, so that the axial conduction is neglected. In that particular case, the temperature along the wall will be uniform. Why is that? So what I was trying to say is, let's say you have you have some pipe like this, and this is and this material that you are going to use for the walls of the pipe, if K of that particular pipe material is very high, then what happens? If the thermal conductivity of that particular material is very high, then what will happen is the temperature along this direction will be very less. For the same amount of heat flux, the temperature gradient will be very less. So if I consider this as my x direction, then Kp times, if you consider the thermal conduction equation, del square T del x square, under steady states, we have del square T del y square equal to 0. And then we will be saying that the thickness is very small, so this term will be neglected compared to this term, because if thickness is very much less than length, then you can neglect this term. So del square T by del x square will be approximately 0 compared to the other term. So the heat along this direction will be Qx is minus K del T del x will be almost 0 when the thermal conduction is neglected, because K is very high, del T del x will be very low, so this will be very less compared to the other direction. So heat will be maximally flowing in this direction compared to the other direction. So what is happening in that case is del T del x is 0, which means the temperature along the wall is more or less uniform for the same amount of heat flux in the same direction. So if this material is replaced with a different material, then you're going to have a different kind of temperature gradient. But here what will happen is this. Alternatively, if you want to impose the uniform wall temperature condition, how would you go about doing this? If I want to do an experiment and I want to have a uniform wall temperature, what would be the reliable way to do that? So if I want to do something like that, I need to have a process where temperature remains constant. Which process will have constant temperature? Phase change. Phase change is a constant temperature process. So all I have to do is whichever way I'm doing the experiment, I have to connect the external wall to a material which is undergoing phase change. Then it will continuously take it without changing the temperature of that surface. So whenever that phase change is happening, that particular wall can be considered as a uniform wall temperature. Or you can also have a system where you have a separate control that will continuously monitor the temperature and then increase or decrease the heat so that the temperature is maintained constant. So it's like use a highly conductive material with heat generation. Either case, you will have constant wall temperature. The next case is that of a constant wall heat flux. This is when you have, say, an electrical heater embedded inside the wall. If the heater is arranged correctly, then the heat generation will be uniform throughout the length of the heater. Then you can consider that to be a constant wall heat flux kind of scenario. But whichever be the case, our objective is to understand what is happening to the fluid inside. So one question that you will be asking is what is the mean temperature of the fluid inside the particular channel or whatever that internal flow that is happening, either a duct or a pipe or any channel. And next obvious questions are, okay, in case of a uniform wall temperature, you'll be asking what is the net heat transfer rate and corresponding to the Nusselt number and the heat transfer coefficient. For a constant wall heat flux case, you'll be asking on what is the temperature. So for this, we'll be asking heat transfer, and for this, we'll be asking what is the wall temperature that can go up to, and Nusselt number and the heat transfer coefficient. Again, obviously, you can also put TW and QW prime here, but this will be directly given from the boundary condition itself, and you already know the electrical heat power you are giving. If you know the efficiency, from that you can directly calculate what is QW prime, and here you can directly measure the TW directly. So these are not explicitly given in our objectives. So our objectives are clear. The next step is we understand this, the hydrodynamic and the thermal regions. So there are different regions within the flow. So if you consider this as the top one is a wall, and then you have another wall on the top and bottom, and then a flow is happening. At the inlet, we have a uniform velocity profile. But what happens is because there is a viscosity, a hydrodynamic boundary layer will start forming here. Similarly here. So initially, these two can be considered as external flows, but then the main difference is this region where you have, again here it will be uniform. If you recollect what when we were discussing this even before, when you have a boundary layer, what happens is initially the velocity will be 0 at the wall, and it will keep on increasing, and then eventually it becomes the free stream velocity. But what happens is that the free stream velocity at this point, and let's say at this point, if you consider, the area has decreased from this point to this point, but the total volume flow rate has to be constant. Whichever is coming should be going in. So which means the velocity here will be higher than velocity here, which means the fluid will accelerate inside this region. This region is called the core region, where the fluid will accelerate, and then what happens is this boundary layer keeps growing, and eventually they will reach a point where both of these will match together, right? So here is the most important point that you need to be considering. So depending on what you are looking, this can be an external and internal flow. So if you are restricting yourself to region very close to this one, so how do you know that is when these two surfaces, the separation between the surfaces versus the length of the walls that you are considering, depending on that ratio, this can either be an external flow or an internal flow. So if you are far into the domain, or where your L is very much high compared to the separation of the plates, then you will be in an internal flow like this and this. But if L is very small, then you can consider these two plates as non-interacting, or basically you can consider the flow to be external and use the boundary layer equations that we derived in the last two. Now here we have two different regions. Let's say we are dealing with internal flow, so the length is very large. So what happens, eventually both of these layers will mesh and then form something like this, where you have this is what we are calling fully developed profile. Once both the boundary layers mesh, even if you look at here, or if you look at here, or at any point downstream, all the velocity profiles will look similar to each other. That is what the fully developed condition means. So to put mathematically, under fully developed scenario, we have the streamlines will be parallel to each other, and then del U del X will be equal to 0. The the hydrodynamic boundary layer will be equal to the radius of that particular channel. We are equal to 0. How do we get this? Yeah, you can take the continuity equation, and then you will say that del U del X plus del U del R, sorry, del U del X plus del V del R equal to 0, and you know del U del X equal to 0, which means del V del R equal to 0. So how do you get this? And I'm saying this equal to 0, which leaves me del V R del R equal to 0. And under fully developed condition, even del V del X equal to 0. So this means VR should be only function of R. So this would mean dVR dr equal to 0. And what are my boundary conditions? If I take any one of the boundary condition, that velocity at the wall has to be 0. So this implies if VR at R equal to R not equal to 0, and I want the derivative to be 0 and the function has to be 0, which will only mean that VR has to be 0 everywhere. So under fully developed conditions, we have VR equal to 0, and then the horizontal velocity, we will have del U del X equal to 0 for fully developed condition, and then the hydrodynamic boundary layer thickness will be equal to R. And we have two regions here. One is a fully developed region where all these conditions are satisfied, and when any of these are not satisfied, we'll call it the entrance region. That is where your delta will be less than R naught. Okay. In the next two lectures, in this week and in the following week, we will be focusing more on the fully developed region. In this week, we'll slightly do the scaling argument for this region and come up with what happens here. What is the Reynolds number? What is the pressure drop? What is the shear stress that is going to happen here? These are the kind of questions that we are interested in now in this region, and similarly in this region. And the most important thing is because this region is, if you see the structure, the fluid flows in this region is completely different from this. Here you have a mix of both internal and external kind of thing. Here you have a completely internal kind of thing. So because it is like this, we need to know how far is this entrance region into the length of the pipe that we are considering. So if you have a long channel or a long pipe, under what conditions, if for example, if I have a 1 kilometer pipe, so out of 1 kilometer, how far does this entrance region is present, and do I have to consider the pressure drop in this region alone, or do I have, or if I assuming it to be fully developed throughout the pipe length is okay or not? Questions like that will be answered only if you know the extent of this region compared to the total length of the pipe. If this extent is very less, then you can ignore this part and only focus, use the fully developed assumptions, use those equations, solve, and then you will be able to predict the pressure drop, friction forces, etc. With a reasonable accuracy. So even to answer that question, we need to first know what is the extent of this hydrodynamic entrance region. Now, if you apply the same thing to the temperature boundary layer, you will again have the same. Initially, the temperature will be uniform, but let's say if there is a constant heat flux, and the temperature will keep on increasing here because you're continuously adding the heat. Let's say it is the heat addition that you're doing continuously. So temperature will increase near the boundary, and this temperature will also keep increasing. So as the fluid flows through the channel, its temperature will keep on increasing because you're continuously adding the heat. This temperature will keep on increasing. Because this temperature is increasing, the wall temperature will also keep on increasing. So here we cannot directly define as we have defined in the previous case. We cannot say that delta del x will be 0 because your temperature keeps changing as you're adding up the heat. So we define something called some other kind of a non-dimensional temperature, which is P, defined by this equation, where phi is Tw minus T by Tw minus Tm. Tm is the bulk temperature or the mean temperature or the across the cross section. If you define phi in this way, then this particular phi will not change as you move across different cross sections. This we will make use of this particular non-dimensional temperature when we derive the temperature profiles a little later. But the key point here is, instead of temperature, if you use this P, all the definitions that we have derived previously will hold. So your del phi del x will be equal to 0 and delta T should be equal to R0. So here we don't have the things like the one that we have before. So delta T by delta equal to 1 by Prandtl to the power half is something that we derived previously. That is valid here, but once you go into the fully developed region, both the thermal and hydrodynamic boundary layers will have merged with each other, and then you'll have a common temperature profile and a common velocity profile. So delta T will be equal to R0 and delta will also be equal to R0 once both of them have matched. So what will Prandtl number determine then? Yes. So the Prandtl number will determine how much is the extent of this region. So depending on the Prandtl number, your hydrodynamic entrance region can stop here or it can stop here, depending on what the Prandtl number is. Right? Now we look at the other boundary conditions. So instead of constant heat flux, you can have constant surface temperature. Then also the profile will look similar. The only difference is near the wall, it has to reach the temperature. So we'll have the gradient here, and everywhere else it should be the same. Here again, we'll define the non-dimensional temperature P in this particular way, and if this del phi del x equal to 0 is what we call the fully developed profile. Now, as I said, the Prandtl number, the key thing here is, before going to the Prandtl number, first let's understand the hydrodynamic length, hydrodynamic entrance region, and then we will see the thermal entry length. For the hydrodynamic length, we know that how do you determine the hydrodynamic entry length? So entry length is the distance in which the external flow kind of assumptions prevail. So which means we can still use external theory, the boundary layer theory that we developed before. So where delta by x will scale as 1 by square root of Rex. Rex is defined in this way. We are saying exactly when the entrance length is matched, then this x is equal to entrance length and delta will be equal to, let's say d is the distance of whatever we are considering. It's basically R0 by 2. So d by h will be approximate, will scale as 1 by square root of ReLH. So if I just do a little rearrangement here, ReLH can be written as um times LH by nu. So I just multiply and divide with d. So this will be Re d times LH by d. So if I do a rearrangement, so this is what I'm getting. So what this means is LH by d is, as I said, the entrance length with respect to the separation between the plates. So this is something that tells me what is the separation between the plates, and this is something that tells me the length of the plate. So this ratio will scale as RE, which scale with the Reynolds number. So for a given average velocity profile, if LH by D is of certain magnitude, so if L is less than that particular, if L is less than this particular LH, then you can consider that to be the hydrodynamic entrance length. Now, if you apply the same argument for say LT, what would change here? Yeah, it's straightforward, right? So instead of delta, you'll be having delta T. X will remain the same. All of these quantities will remain the same. So what would delta T by X scale as? Right? It will scale as square root of Rex times P. This additional term is because the delta T by delta is 1 by square root of P. So if you want one step ahead, you just want to decompose this. So this is basically delta T by X is delta by delta T times delta by X. We know that delta by X will scale as, so the first one is 1 by Prandtl to the power half, and the second one is 1 by Rex to the power half. That is what we are writing here. Again, we can do the same analysis. The X will scale as LT and delta T will scale as T. So if you substitute that, so previously we had just the Reynolds number, now you'll have the Reynolds number times the Prandtl number coming up here. So the order of this is in the mag is below, this will scale as in the order of 1. And the most important parameter, as I said before, is LT by LD will scale as Prandtl number. So what can we make from here is, depending on the Prandtl number, the entrance region for hydrodynamic and the MLS can different. If you have a low Prandtl number fluid, like say Prandtl number less than 1, like an air or something, LT will be less than LD, which means the thermal boundary layers will match first or will match faster than the hydrodynamic boundary layer. But if you have fluids with higher Prandtl number, like oils or some paraffin kind of stuff, where you have a high Prandtl number, then what would happen is LT will be greater than LD, or the hydrodynamic boundary layers will match faster, and then the thermal boundary layers will match. Why is that important? So why do we have to know this thing? So knowing this thing, we can make some assumptions as to the type of flow, which we will see in the next week. When you have, for example, let's say Prandtl number is less than 1, or let's say let's assume Prandtl number is greater than 1. If Prandtl number is greater than 1, then LT is greater than LD, which means if I am dealing with a fully developed profile for just the thermal boundary layer, if I know that thermal boundary layer is fully developed, then I'll know that the hydrodynamic boundary layer would have already been formed by that time, and I can use the velocity profile from the fully developed case to solve the equations for temperature if Prandtl number is greater than 1. If Prandtl number is less than 1, then what would happen is the LD is higher, which means then I will have 3 regions. So you say this is LT, and if this is LH, this is for Prandtl number less than 1. So for Prandtl number less than 1, if I am solving for a fully developed temperature profile, there still exists a region where the velocity has not been fully developed. So I have to solve for the velocity profile here to be able to use it inside the energy equation. But if it is, then I have to specifically say that I am solving only in this region. So if I am using fully developed thermal and hydrodynamic boundary layers, then I will be restricting myself only to this region where I can use such kind of equations. However, if Prandtl number is greater than 1, then this would be exactly opposite. So for Prandtl number greater than 1, maybe I'll sketch here. This will be LH, This will be LH and this will be LT. So if I'm solving for a fully developed thermal profile, then obviously it will be fully developed in the hydrodynamic case as well, because after this point it is fully developed in the velocity. So I can use the fully developed velocity to solve my energy equation. This is for Prandtl number greater than 1. Right, knowing the Prandtl number can help in that way. Okay. Are there any questions up until here? No. Okay, the question now is, okay, we said that it will scale as 1 and the other one also will scale as 1, but we do not know the exact values of this. So the next obvious step is to find the values of this, find the value of this particular number that we are having here. And people have done some numerical simulations and they came up with some values, let's say CH and CT. So you assume this scaling and then find this value from the data that is available to you, like fit a correlation and get the value of CH. Depending on different geometries, you have different values of this. This is not a constant, universal constant. This particular value will keep changing depending on the type of geometry you are having. So for a rectangular geometry with this particular dimensions, CH and CT are CH is basically of this and CT is this value. If you have a circular geometry, you will have a different value of this coefficient. Again, these coefficients will change for every geometry, so it is kind of dependent on the geometry. Let's take a simple case where you have to determine the extent of entrance region in the above in a rectangular duct of this cross section where A equal to B of a air if it is at 25 degrees Celsius and flowing at 1.5 meters per second through it. Take that A to be 1 meter and B will be half. So it's a duct, let's say an HVAC duct where you have that is carrying air at this particular velocity. So what would be the length of extent of the entrance region, LH? So I'm asking you to find, say, the LH value. And another important parameter here is something called DH. What is this DH? DH is what we define as the hydraulic diameter. So the hydraulic diameter is defined as 4 times area by P, where P is a wetted perimeter. Wetted perimeter is basically the total perimeter that is exposed to. So if I cut a cross section, here, what is the wherever the fluid is touching, let's say you imagine a string that is passing through all the points where the fluid is touching, then the length of that string is basically the wetted perimeter, and AF is a cross sectional flow area. So this is my duct, so this is a cross section. So if I have a duct like this, and I'm making a cross section, so the cross section is taken here at some point. So wherever the fluid is touching, the length of all of this is this perimeter, and area is basically the area of this. That will be the area of cross section. So that quantity is the hydraulic diameter. So the main idea behind introducing this parameter is this quantity is to help you, even with different geometries, we can come up with some number to relate this particular way. So otherwise what we'll be having is, for example, if you have a circle, it will only depend on radius. If you have a rectangle, it will depend on A and B. If you have different geometries, require different number of constants to determine to fix the geometry, which would make the problem a little more complicated. So what people have done is, okay, we will represent the entire geometry with one number, and that is this hydraulic diameter. So once you fix the hydraulic diameter, then you will get a constant of this. So this in this way, what happens is this particular constant that you are getting is fitted against different geometries. So for even if it's a square, rectangle, different cases, all of them will have the corresponding DH, and then you will get a CH correspondingly for that. This is some kind of a universal way, so you don't have to worry about which way or which way you have taken, but convert it into this and then use that particular dimension. Okay, coming back to the problem. So what is the first thing that we have to do? So you know the A and B values. So you have to determine AF and P, from that calculate DH. You know U and mu, so you can use that to calculate the Reynolds number. From that you can calculate the LDH value. These are straightforward. So D is for AF to P, AF is A times B, where perimeter is 2 times A plus B. So if you substitute that, so I'm getting 2 by 3. Once I have the DH value, I can calculate the Reynolds number. Oh, sorry, I think the velocity value is given differently here. Reynolds number you will be calculating. This value is less than 2300. This implies that is a laminar flow. So whatever we are using up until now can actually be used. Then we'll substitute in the equation. The CH value is given here. So if you substitute that, you're getting a length of around 60 meters. This is a straightforward problem. Let's solve another problem. Let's say I have an annular cross section. So the fluid is flowing in this region. The fluid is flowing through the cross section or through the pipe, or it's like the inner region is kind of filled with solid, and only in this annular region is where the fluid is flowing. And I need to find the hydraulic diameter. You can use the relation that we derived just now, like I have defined just now, 4 times area by perimeter for this case, and tell me what is the value of hydraulic diameter. Yeah, so I hope you have solved it. What's the value you're getting? So area is 5 times rho square minus r square. You have to just take the cross section area, and the wetted perimeter is the perimeter is basically wherever the fluid is touching, you have to include that in the perimeter. So it is touching in two different places. So it is touching on this perimeter, which is 2 pi ri, and it is also touching on the inner of the outer surface, which is 2 pi rho. So that will leave me with 2 pi of rho plus ra. So if I substitute, the hydraulic diameter is 2 times rho plus ra, right? Okay. Now we'll have two different cases, as I said before. One is a uniform wall heat flux, and then comes a uniform wall temperature. Now let's take the first case where you have a uniform wall heat flux. So in this case, what are our objectives? We have to determine the total heat transfer rate, what is the mean temperature variation, and then we also need to know what is the wall temperature variation. These are the three quantities we are interested in. So total heat transfer rate is a straightforward one. So you know the heat flux, QW prime, and we are saying that it is constant. So how do I calculate total heat transfer rate? You have to just multiply with the total area that is available. So I am considering it as a total perimeter times whatever is the x that you are considering. If it is here, then it will be area up until here. Depending on where the x is, this area keeps increasing and the total heat transfer rate will change from that. Now the next one is the we need to find the mean temperature variation. So for that, if you assume a steady no heat generation kind of process with negligible kinetic and potential energy changes, you also neglect the axial heat conduction, as I said before, when you have a highly thermoconductive material, and then the heat transfer is only happening along this direction compared to the other direction. Then what we can see is the net heat flux, if you consider any region, is QW prime times Px up until there. And what is happening to all of this heat? All of this heat is absorbed by the fluid, so it should raise the temperature of the fluid. So if the temperature here is Tmi, then it will be Tmx minus Tmi, where m dot is the rho times a times velocity. And from this you can determine what is the value of Tmx. So you can see Tmx here is varying linearly with x, because this constant, like if you have a uniform cross section channel of uniform cross section area, perimeter is constant, m dot is constant, Cp and Qw prime all are constant. So when all of these are constant, then Tmx is a linear function of x. Now what happens to the wall temperature? So this is the mean temperature. So what happens to the wall temperature? So in order to do that, we need to determine the heat transfer coefficient. Now the heat transfer coefficient is defined as QW prime by TW minus Tm. So we know this is a constant. So from this I can determine the wall temperature. So if I take the term over here and m to the right hand side, so TW will be Tm plus QW prime by Hx. So somehow we have to find this h of x. If I know h of x, then this is constant, and adding this to a linear function will give me TW of x. So what will be this h of x? Is a question that we'll be answering a little later. So if you just substitute the equation for Tm also back into this, so TW of x is given by this expression. Tmi plus Qw prime into this whole term. So if this h of x is constant, which is not a function of x, so in the fully developed region, where we'll see little later, that once you enter the fully developed region, the heat transfer coefficient will become constant. And once it becomes constant, this will be a constant term, and that will get added to constant term plus this thing. So this will be a linear function of x. So the wall temperature will linearly vary, and the mean temperature will also linearly vary with the length of the channel. Okay. Now we'll go to the next case where you have uniform wall temperature. So when here objectives are again the same. You need to find the total heat transfer rate, except for the last objective. So previously we were interested in finding the wall temperature, but now we know the wall temperature, so we'll be interested in finding what is the heat flux variation across the wall. The first one, here we'll start with taking arbitrary elementary volume, where you have dQW that is coming from the wall, and the fluid is flowing. So here it will be Tm, and it will change to Tm plus dTm by dx times dx. So if I apply an energy balance, so whatever is coming in should be absorbed by the fluid. That it will be m dot Cp times dTm should be equal to dQW. But we also know that dQW is comes from the other side, and that is coming because of the transfer, and we have defined the heat transfer coefficient in such a way that h times dW minus dx times the area, which is the total perimeter times dx, should be equal to dQW. And now if we equate these two terms, we can write in this way, and if you integrate it, we'll have something like if you are already familiar with the heat exchanger concepts, then this is something very similar to the LMTD expression. So where the temperature will vary in this particular fashion, where this h bar is the h bar x, h bar is some average heat transfer coefficient across that particular length, wherever you're considering. So depending on the x that you're considering, this h bar times x will keep changing. But the idea here is the temperature will vary exponentially. It will eventually, what will happen is this exponential term will go to 0, and Tm will be equal to wall temperature. So beyond that point, beyond the point where Tm reaches Tw, once Tm becomes Tw, then the profile will be kind of the heat addition will. So if you imagine, so the temperature is something, if wall temperature is higher, so if it will be something like this, and then what happens is it will keep increasing, and eventually this is the asymptotic case where the wall temperature and the mean temperature will be the same, like it will be uniform temperature. This will happen at infinite length. Obviously, in practical scenarios, we won't be having infinite pipes or stuff, so it will be somewhere in between, and you can use this expression for that. So this is the mean temperature variation. Now what happens to the wall heat flux? Total heat transfer rate is m dot Cp, whatever is the final temperature minus the initial temperature, and heat transfer is h times Px times this. Again, here we need to determine the heat transfer coefficient. Only if we get the heat transfer coefficient, we'll be able to find this. And we need this heat transfer coefficient again to solve for Tmx also. Like to solve for this or this, we need to know the heat transfer coefficient. So how do we get heat transfer coefficient? Again, we will solve the energy equation. We will take the energy equation and then we will solve it. So a quick thing for you to ponder over is we in the last few lectures we have we discussed two different kinds of methods. One based on differential and the other one the integral techniques. So again, all of this is based on differential technique. You can also use integral techniques. You can assume a velocity profile, put the boundary conditions, solve the momentum integral or the energy integral equations. But then the energy integral equations, how will you solve in this particular case? Is something that you have to think about. The main difference between external and internal flows is when we were doing the integration in an external flow, we were doing it from 0 to delta. Because after delta, all the quantities will just go to 0, so there is no point in integrating it beyond delta. But what will happen in this case? Give it a thought over, and then maybe we'll discuss next week if one of you can come up with what could happen in that scenario. So to summarize, we can have either a constant heat flux or a constant wall temperature. Depending on in this case, you'll have the linear variation of the mean temperature, and here you'll have an exponential variation. So again, I just separated it. So this is only the fully developed region. Inside the fully developed flow region, you'll have constant or a linear temperature Tm and linear temperature Tm. The difference is the constant. Again, we are drawing this assuming that, if you remember, when we were defining this particular quantity in the variation, we had one more term here, right? For TMX, it's not a problem. For TWX, if you recollect, we have one more term plus 1 by h of x term. And now only if that h of x is constant, then this particular thing will be constant. So we will see, and that h is constant only in fully developed region. So that's why this assumption is coming here. Now for the other case, it will exponentially vary. So at infinite length, this Tm will eventually become equal to Tw. Maybe I should have drawn it that way. Are there any queries up until here? Good. Now, up until till now we are saying mean temperature, mean temperature, mean temperature. We have not defined it in any way. How do we define the mean temperature? Is the mean temperature is basically the energy average fluid temperature across the channel. So to put mathematically, its energy average is integral rho Cp U times TdA divided by m dot Cp. So, or in another words, m dot Cp Tm is basically equal to this quantity. So m dot is rho A times um. If the properties are constant, then rho Cp here, rho and these things will get cancelled off, and you will be left with this integral. So this is my mean temperature profile. If you have circular pipe, then you have to integrate from 0 to R naught, and this will be TR. If it is a parallel plate channel, instead of this, you will have dy times the width of that particular channel. As I said when we started in the beginning, we said that in fully developed, in thermally fully developed region, in a thermally fully developed region, what would happen is we define some non-dimensional temperature that the derivative of that with respect to x is going to be 0, and that non-dimensional temperature is Tw minus T by Tw minus Tm, and we are saying the derivative of this equal to 0. So when you apply the chain rule, and then this is the equation we'll end up with. So del T del x is dTw by dx minus p times r times del dTw by dx minus dTm by dx. Both Tm and Tw are only functions of x, while T is a function of r. So this entire term will only be a function of r in fully developed region. In the developing region, it could, in the entrance region, this could still be a function of r and x. But once it is fully developed, we are assuming del phi del x equals 0. So phi will only be a function of r. Now we will have the two different cases that we have derived before. So uniform wall temperature and uniform heat flux. When it is uniform wall temperature, dTw dx will be equal to 0. So you have del T del x equal to Cr times dTm by dx. And when it is a uniform wall heat flux, then we know that Qw prime is h times Tw minus Tm. And we are using another fact here. So how did we come up with this? This Qw prime. And if in fully developed region, which I said before, I've not proven that, which again we will take up in next week, that this h is also constant. This is the first thing we will derive in the next week, that h will be constant in fully developed region for a uniform wall heat flux. If h is constant and Qw prime is constant, then this particular quantity will also be constant. And since this is constant, dtw by dx should be equal to dtm dx. So when both of these terms are equal, then del t del x should also be equal to dtw by dx. So all of these terms will be equal, and they will be equal to the term that we derived previously, dtm by dx equal to tmi plus this particular quantity. The derivative of this will be the quantity here, this quantity. Okay, are there any questions? Okay, then let's solve a simple problem. Consider you have a flow through a pipe with uniform wall heat flux. If wall temperature is changing from 25 to 45 across a length of 1.5 meter, determine the bulk mean temperature at the outlet if the bulk mean temperature at inlet is 20 degrees Celsius. So the inlet mean temperature and wall temperature at inlet and outlet are given, and the bulk mean temperature at inlet is given, and you're asked to find what is the bulk mean temperature at the outlet. And we do not know what is the net heat flux that is added. How will you go about solving this? Assume that all the properties are measured in fully developed conditions. Yeah, so you'll use the same relation that dw by dx should be equal to dtm by dx, that should be equal to this, and all of them have to be some constant because it is a uniform wall heat flux. So the derivative have to be constant. So if the difference here is 5 degrees Celsius, the difference at the outlets will also be 5 degrees Celsius. So if it is from 25 to 45, this will be from 20 to 40. The straightforward thing. Now comes the important questions of what happens to the heat transfer coefficient and the Nusselt number. So how do we determine heat transfer coefficient? Is the K times delta del R should be equal to H times Tm minus Tw. Just observe the notation that we are using, the sign convention also. The heat flux is given by H times Tm minus, this is from the fluid. The heat transfer is happening from the fluid to the wall. So this is H times Tm minus Tw should be equal to this. Or if you are convenient with the same notation that heat will be transferred from the wall into the fluid, then H times Tw minus Tm, whichever notation you are comfortable with, K times delta del R at R equal to R naught. When you're writing like this means that fluid, the heat transfer is happening from the wall into fluid, whichever way you're comfortable with. And from this, you can write the expression for H as this. And now if we choose the arbitrary scales that T will scale as delta T, so those both the terms will cancel and H will be in magnitude of this. H will be K by delta T. So the most important thing, or without the derivation, we can understand from here that H will scale as K by delta T. And you know that once it reaches fully developed condition, then what happens is delta T will become constant, and that will be equal to the half the channel separation, the separation between two walls. So if delta T becomes constant, K is a constant, so H becomes constant, right? It doesn't matter whichever boundary condition you are considering. So this is the scaling that you will eventually end up with. That is why we were using the same thing before. We will derive the exact relation in the next week, but for now the argument is clear, I guess. I guess the argument is clear because in a fully developed condition, delta T will become constant, so H will become constant. So same applies. Once H is constant, then the Nusselt number will also become a constant. Of course, in the developing region, what would happen is this delta T will be a function of both the Reynolds number and Prandtl number. So whatever relation we were having previously will prevail. So Prandtl to the power half, RE to the power half. So, and then we'll have an additional term that will, what will happen to this term is as the x will keep on increasing, this term will keep on going off, and then eventually the terms will cancel, and then this will become constant. So this will become of order 1. Right? In the entrance region, it should be function of this d by x, and as the length increases, it should not become a function of that. Yeah. So I think up until here there are no questions, then we'll move on to the next one. So now the objective is, okay, we have to solve the energy equation eventually, but in order to solve the energy equation, we have velocity terms inside the energy equation. So u times del t del y, u times del t del x plus v times del t del y. There we need to find the velocities u and v, only then we'll be able to solve the energy equation. So the simplest possible case that we can consider is between two infinite parallel plates. So this is called the plane Poisson flow, where you take the equation and then now we'll simplify it one by one. So we assume steady, so this term will go off. In fully developed case, this term will go off. and here v will be equal to 0 as we derived previously that v are equal to 0 for a fully developed case. So all these terms are gone. Now we have the pressure gradient and the viscosity terms. So again, this term will go off in a fully developed case. We are only left with this. So u will only be a function of y. That is what we, that is how we define the fully developed flow. And then p is not a function of y because v is 0. The y momentum equation, all the terms will be 0, and you will be left with del p del y equal to 0. So which means p is only a function of x. So this is what we are left with. And the boundary conditions are velocity has to be 0 on both ends of the ball. So if you solve that, the velocity will be given by this expression. Now depending on the pressure, on the gradient of this sign of this, you can have different cases. What is the characteristic number that you will be using for this case? Yeah, we discussed before. We'll use the average velocity for that. So we need to determine average velocity. So that would be the first one. So to determine the mean velocity, we'll define this q is um times a, and that should be equal to integral u times w dy. So if it is circular, then it will be 2 pi r times dr because it is parallel plate channel. So it is whatever is the width times dy. So if you do the integration, so I'm getting um as this particular quantity. From this, you can determine what is dpdx and substitute that back and into the velocity equation. So you'll be left with this expression. And you can say that when y equal to 0, that is where the velocity will be maximum, and that is what I am writing as umax. So umax and the mean velocity are related in this way. Obviously, the next questions are what is the shear stress, what is the next net drag force that is acting. All these questions will come obviously later. So the first one is the shear stress, which is tau w is mu times du dy. So if you substitute that, so I'm getting a value of 3 mu m by h. Now here there are two things. One is the skin friction coefficient and the other one is the friction factor. What is the difference between these two? So previously when we were having the external flows, we were only discussing something called skin friction coefficient because all that we mattered there was just the shear stress. Because it is a flat plate, what happened was the pressure was always constant. We assume the pressure to be constant. There is no external pressure gradient. So we have not needed any two different quantities. All we needed was the shear stress. That's why we had this one coefficient, the skin friction coefficient. But now here what happens is we have two things. We have the shear force that is acting here, and then there is a net external force, that is the pressure gradient that will be happening across the length of the channel. So we have two different numbers here. One is the friction factor, which will relate with the pressure gradient across the channel. So that is minus del p del x by half rho un square, and this particular quantity is 24 by REH, where REH is defined in this way. So just keep a note that this total channel separation is 2H. And then skin friction coefficient, this is again with respect to the shear stress. So if you want to find the shear stress, you need to calculate the skin friction coefficient, like first calculate the Reynolds number, calculate the skin friction coefficient, multiply with this. If you're interested in finding the pressure gradient term, then you have to use the friction factor. So you can see here that friction factor is 2 times CF. So if you use the wrong coefficient, then you'll be off by more than 100%. Is that clear? Now we'll extend the same idea for different cases. So this is two infinite parallel plates. So the next thing that you can consider is something called fluid flow. This is again in the simplest flow, where you have one plate at rest and the other plate is moving with a constant velocity u. So here the condition that we are imposing is this constant velocity. So previously what we were doing is we are keeping a pressure difference across the inlet and the outlet. But now what we are doing here is we are imposing a velocity here, and we are assuming that the pressure is kind of constant throughout. So del p del x equal to 0. Then all you have is this one equation with this boundary condition. So this you will get a linear profile. Then shear stress and everything is straightforward. Again, here as I said just now, that dpdx is assumed to be 0. So there is no pressure gradient across the length. So there is no point in defining a friction factor for this particular flow. All we have to know is the skin friction coefficient, which is the ratio of the dynamic wall shear stress to the dynamic pressure. So this will give me 8 by REH, where again REH is defined in this way. Keep a note here that we are using U here, not UM. Because in the previous case, UM is the thing that we can measure. Here we can measure U directly because we are imposing the velocity. You can directly measure this one. So you have to use that particular U as your characteristic velocity. H is the plate separation. Previously it was 2H, here it is H. In the next case, you can have is a Hagen-Poiseuille flow. This is where instead of two parallel plates, we'll have a circular cross section. So maybe I should have drawn something like this. So you have a circular cross section. This is radius r. So here again v is 0 and use a function of just r, and it is fully developed. So del u del x will be equal to 0. If I take my momentum equation, so 0 is minus del p del x plus this particular term. Again, if you take the other equation that we are assuming this to be axis symmetric flow, which means nothing here is a function of theta. It's only a function of r. So if you solve this equation, you will get u as this particular quantity. Here again, we have two different cases. It is a straightforward one. So we see if the pressure is higher here and lower here. So if I say this is P1 and P2, if P1 is greater than P2, then if I take the gradient del P del x or dp dx, along the x direction pressure is decreasing, so this will be 0. But because P1 is greater than P2, flow will happen from left to right, so this is favorable. And comes the other case when P1 is less than P2, then what will happen is flow will happen in the reverse direction. So flow will happen from here to here. So all that you have to do is, depending on the sign of this sign will change and velocity will reverse. So these are the terms you have will use again sometime later. The favorable and adverse pressure gradients. Mean velocity is defined in the same way as we have defined before. So integral u times. So previously it was the w times dy. Here it will be r 2 pi r times dy. I have just taken out the 2 pi term here. So if you do the integration, so this is what you will be getting. So ur is given by this particular term. Here u max is 2 times u. Previously it was 3 by 2 times. Now it is 2 times u. Where um is the mean velocity. Now once we get the velocity, the next again here we have a pressure term again in this picture. So here also we will be requiring two different numbers. So we have to find wall shear stress, and then we have to find the friction factor and also the skin friction coefficient. So first we'll calculate the shear stress, which is mu times du dr at r equal to r naught. If you substitute take the derivative of this, and it will be 8 mu um by 2 r naught. So once you have the shear stress, you can calculate the skin friction coefficient. That is coming out to be 16 by RED, where RED is again this particular quantity. D is your hydraulic diameter you can take, and that will turn out to be capital D. Now the friction factor, or which is also called the Darcy's friction factor, is with respect to the pressure gradient. This is that is coming out to be 64 by RED. This is a very important relation which we'll keep using later. So how can you use if you relate this F with the skin friction coefficient? So the friction factor is 4 times the skin friction coefficient. So the error will be even higher if you use the wrong coefficient. So skin friction is to understand, just as the name says, is about the shear stress, or basically skin is basically where the drag happens. So use CF when you are intending when your intentions are to find the shear stress. But if your intention is to understand what is the pressure drop across the channel length, then you have to use the friction factor. I think the difference is clear, so please don't confuse between these two quantities, because tables will be provided for this and this separately. You have to use the correct table to calculate the corresponding force. We are halfway into the session, so if you have any queries, you can just unmute yourself or type in the chat box. Okay, I guess there are no questions. So let's solve another problem. So it's just like the previous one. The only difference is we'll consider an annular channel now. So have two different radius, inner and outer radius. So I'll wait for say, maybe I'll give you 5-10 minutes. Use the same equation that we used before, and then determine the velocity distribution for a fully developed case. So the governing equation and the boundary conditions are shown here. You can assume dpdx to be constant. That is another assumption that we are taking, that the pressure gradient that you are imposing is constant. Okay. Hope you solved it. Yeah, the only thing is in the previous case when we were substituting the boundary conditions, it's just a matter of algebra. So you have to substitute the correct boundary conditions. So previously when we were solving for circular pipe, we had assumed that the u has to be constant, u has to be finite value at r equal to 0. So we had made c1 equal to 0, but which is not the case in this particular problem. If you determine the c, when you substitute both these boundary conditions, you'll be able to find c1 and c2 and then get the expression for u of r. Though I have not done it here, you can also, if you're interested, it's again the next straightforward questions once you do this are determine what is the mean velocity, where the maximum velocity will happen, and then the other questions are what is the shear stress on the inner wall, what is the shear stress at the outer wall, are both of them equal or not, and again determine what is the skin friction coefficient, what is the friction factor. These are all other questions that you can come up with. Now this case is very similar to the Hagen-Poiseuille flow. Now we can also have a different case which is quite similar to your fluid flow. So what can happen is the Taylor fluid flow. So what happens is you can make one of this to be rotating inside another one. Let's say this is kind of scenarios which happens in case of journal bearings and stuff, where the outer one will be a fixed one, and this will be a shaft, and inside you will fill this with some lubricant. So this shaft will rotate, and because of this rotation, you'll have some forces and other stuff which we will not discuss. But the point is, what you are required to find is, let's assume that this moves with a constant velocity or constant omega, and then determine what is the velocity distribution that you are going to have here. So everything will be similar to this one. The only difference is you can assume dpdx will be 0. There is no pressure gradient imposed in that particular problem, and the boundary conditions will change. So at r equal to Ra, you'll have u equal to Ra times whatever is omega that it is rotating with, and at the other end you have u equal to 0. So these boundary conditions will change, and this dpdx term will go, and then you can solve this governing equation and get the velocity profile. That could be another problem that you can try solving for. And in that problem, the question that is important is what is the shear stress that is acting, because we want the shaft to be supported. So that's why we kept the bearing in the first place. But at the same time, we do not want to spend so much energy to be wasted in just this drag force. So you can compute what is the net drag force that is acting on the shaft, and you can come up with, once you get the expression, you can think of which terms you can use to actually reduce the friction force. Things, questions like that can be answered later. So that could be another problem. I have not included here. You can solve it for yourself later. So let's take a very simple case. Instead of taking that full like Hagen-Poiseuille flow, let's consider the plain Poiseuille flow, and you can find out what is the net power required to overcome the viscous resistance. How do you define the power? It's basically force times velocity, or in other words, delta P times the volume flow rate should give you the power formula. So I think I've not discussed this, so maybe I'll just show you the equation. So basically the power required is force times velocity, or you can write it as force by area times velocity. So this is basically your delta P that you are applying, and AV is your volume flow rate. That is how you can get this power expression. So just determine the power required. So you know delta P is basically, if there is a linear gradient, so this will be whatever is the gradient times the length of that particular point, length of that particular pipe. Q is A times UM. So for a plain Poiseuille flow, what would be the power required? You have to just multiply these two terms, and you know what is dP by dx for a plain Poiseuille flow in terms of UM. So if you substitute that, this is the equation I'm getting. So what are the conclusions I can make here from this is, if you want to reduce the amount of loss in the power that is required to maintain a given flow rate, all you have to do is increase the suppression and use as smaller pipe as possible, and as smaller length as possible, and increase the separation between the two plates. If the plates are separated far from each other, then the net power will also be lower. Obviously, this is not a more interesting quantity. The more interesting quantity is what is usually what we have is you have to give a specified flow rate that is fixed. So it is interesting to see what is the power per unit flow rate. So then you end up with this thing. So you can see the H is like this quantity is more dependent on H than this one. So by increasing by 1 unit of H, you will be so if I double the separation, then the power per unit flow rate will be reduced by 1/4. But this will only suggest that it will reduce by half. But this is a more interesting or a useful quantity in that sense. That H is that this power consumption is highly dependent on the H value, on the separation between the plates. Okay, are there any questions? Yeah, no questions. Then we can move on to the next problem. So this I have already discussed. Which of these two non-dimensional numbers you would use in a plane wave flow? Yeah, we've already discussed. So you'll be using U because that is something that you measure, or that is something that you have a direct control over instead of measuring UN. So you pick the first one. Of course, in Poiseuille flow, you do not know what is this U directly. All we know is the average velocity, so we'll use UM instead of U. The next one is again based on the relation that we've derived previously. So for the wall temperature, so the mean temperature will keep on, for a uniform wall temperature case, and the mean temperature of the fluid will keep on increasing from the inlet temperature using some particular form that we have already derived. So in that particular case, what will be the as per this relation? So what is the distance beyond which it will reach 95% of the wall temperature? You have to just substitute that value here, and then you'll be able to come up with the equation. Again, the point here is if you assume it to be fully developed, let's assume that after a particular point that this particular length will happen beyond a fully developed, then what can I do is this H will not be a function of X, because if you assume then this particular quantity will be H times that particular length, and from this you can calculate H. sorry, you can calculate L, right? I don't think there are any questions in this. So these are the problems I have for this week. If you have any further questions to discuss, or if you have any doubts, we can discuss them. If not, then we can call it a day for this week, and then we'll meet next week. So next week, the main things that we'll be discussing are on, okay, what exactly is the H? Now we know that H is constant, but we do not know what is the value of this constant. So we'll use the same energy equation, the differential equation that we have, and then we'll solve that equation to find the value of H. And in order to solve that equation, we need to know the velocity values. Those are the velocity that we have derived in this session. The different cases, we have the plane Poisson flow or the Hagen Poisson flow, or the plane QA, depending on different scenarios. You can use the corresponding velocity profile. And again, for the specific case, whether Prandtl number is less than 1 or greater than 1, you'll pick that velocity profile, use that. Under fully developed conditions, you will determine the temperature profile. Once you have the temperature profile, then you can calculate the heat transfer coefficient. And once you have this, then you can get an exact value for this, like you'll be able to solve for this length directly. So what is, from an engineering point of view, why is this length important is, depending on whatever accuracy you have, there is no point in having a length of your channel to be higher than this length, because anyway it reaches 95% wall temperature. So beyond that, the amount of heat addition will be negligible. So we will see what is the heat transfer distribution also. The QW prime, what happens to QW prime for a constant wall temperature case, and questions like this will be answered in the next week. To summarize what we have discussed in this week, so we started out with what is an internal flow and how is it different from an external flow. We discussed on the Reynolds number, the characteristic Reynolds number for this particular internal flows, and then we identified, okay, there are two different boundary conditions that can have for internal flows. From a velocity point of view, there is only wall boundary condition. Then from a temperature point of view, energy point of view, have two different boundary conditions. We can either have a constant wall temperature or a uniform heat flux. And then we identified some of the objectives that we need from this. Then we have seen what happens, how this internal flow is different from an external flow for a channel case. Inside a channel, when we observe two different regions, a fully developed region and an entrance region, depending on whether the boundary layers have mixed with each other or not. If they are not mixed with each other, then we define it as an entrance region, and then if they are fully mixed with each other, then we define it as a fully developed region. And then we came up with criteria to mathematically identify whether that particular one is a fully developed region or not. And that's where we have defined the quantities, like the derivative along the x direction should be equal to 0. And depending on whichever the boundary condition is, for velocity it is straightforward. But when it comes to temperature, the temperature will keep on changing along the x direction. So we cannot say del T by del x equal to 0. So we observe that we have to define some non-dimensional temperature, and then we will use the derivative of that temperature along the axial direction to be equal to 0 to make this as a criteria for fully developed case. We have done that for both constant wall temperature and also constant heat flux. And then we identified, okay, and then we understood that we need to know what is the extent of this entrance region compared to the total length of the region. And in order to do that, we use the scaling analysis again. We know that in the entrance region, the boundary layer still exists, so we can use the same scaling laws that we obtained from the external flows. And with that scaling law, we got an estimate for what is the length of this entrance region for hydrodynamic as well as thermal boundary layers. And we identified that order to be 1 for this particular, for the thermal, it will depend on the Reynolds number times Prandtl number, and for the hydrodynamic, it will only depend on the Reynolds number. But to define this, we introduced a new parameter, and the ratio is different to Prandtl number. Depending on Prandtl number greater than or less than 1, you can have the fully developed region either to the left or right of that. And when we are defining all these quantities, we introduced a new thing called the hydraulic diameter, which is 4a times p, 4a by p, and this will be useful to determine these constants. So for a given geometry, this value will be constant, and then we solve one problem on this. Then we are interested in finding some of these values without actually solving the equations. So to come up with some arguments as to what these values can be. So for a constant heat flux, the total heat transfer rate is this multiplied by total area that is available. And the mean temperature variation, we found out that it will be uniform, it will be linear. The same goes with the wall temperature. Now, when we apply the same analysis for uniform wall temperature, we took an elemental volume and then we try to apply an energy balance, and from there we determine that the temperature, the mean temperature will be varying exponentially, and it will reach the wall temperature at infinite distance. And from this, we also determine what the heat flux variation could be, and in order to determine the heat flux variation, we need to know the heat transfer coefficient, and then we apply the scaling analysis, where we observe that the heat transfer coefficient will be a function of k by delta t, and in fully developed region, delta t will be constant. So this h of x will not be a function of x anymore. Then this will become constant. So Tm at infinitely apart, Tm will become Tw. When this becomes Tw, Qw prime will be equal to 0. This is what I was to try. As if you have an infinitely long plate, then beyond a particular point, the amount of heat radiation will keep on diminishing. So there is no point in increasing beyond a particular point. So these are the profiles that you have for temperature in two different cases. Here, this h equal to constant will happen only in the fully developed region, because h will scale as 1 by delta t, and delta t will be constant only in the fully developed region, and then you will have the constant temperature difference like this. The same logic applies here as well. Then we identified or precisely defined what the mean temperature is. The mean temperature has to be defined in this particular way. Depending on circular or parallel plate, the dA will accordingly change. And we came back to the precise definition for the dimensionless temperature phi, which is Tw minus T by Tw minus Tr. And then for a fully developed condition, we need Phi or del Phi by del x is 0. And once you substitute that, you obtain two different relations. The del T del x is related with the other derivatives in this particular form. And depending on either uniform wall temperature or uniform wall heat flux, you will end up either with this particular relation or the other one. And this equals to constant. And then we solve some problems. These are the scaling analysis for the heat transfer and the Nusselt number. That both of them will be constant in the fully developed region, and when you are in the entrance region or the developing region, then they will be function of Reynolds and Prandtl number. And these powers are very similar to what we derived for the boundary layer flows, just that it will be 1 by 3 instead of 1 by 2. Just keep a note of that. And then comes the important question of knowing the velocity profiles to be able to solve the energy equation. So first we solve the momentum equations for different cases. We started with the plane Poisson flow, where you have two infinite parallel plates and then flow is happening between them because of an imposed pressure gradient. So once we solve this equation, we get a profile that is parabolic in nature. And once we have the velocity profile, the next obvious questions are determine what is the mean velocity, and then find out what is the wall shear stress. And because we are imposing the pressure difference, we have a new number, that is the friction factor. This is something new that is introduced here, which is not there in external flows, because in external flow, all we care about is the net shear stress or the net drag force. So in that case, all we care is skin friction coefficient. But because here we are imposing the pressure gradient, we need to know how much pressure gradient to impose to get a certain Reynolds number and so on. So that is where the friction factor will come into picture. So this is a plane Poisson flow. The next case is, instead of fixing both the plates, we move one of the plate with a constant velocity instead of imposing a pressure gradient. In that case, we have a different Reynolds number with characteristic velocity that is given by the boundary velocity that is given here. So there, here, since we are not imposing the pressure gradient, all we care about is the skin friction coefficient, and that is given by this relation 8 by RH. Now, all of this is with parallel plates. So extending this to a cylindrical case or a circular cross section is where we have the Hagen-Poisson flow. We take the same governing equation with an imposed pressure gradient del P del x. So if you solve the equation, you will get a profile like this. And here, depending on this positive or negative, the flow can happen to either to left to right or right to left, depending on whether P1 or P2, whichever is greater. It will happen from the greater to the smaller one. So once we have the velocity, we'll determine the mean velocity, and then we identify what is the shear stress, skin friction coefficient, and the friction factor. This is an important relation. And both of these have to be used appropriately. So skin friction is used to calculate the drag force, while friction factor is used to understand what is the net pressure gradient that you have to impose to drive the flow. And then we discuss some problems. I guess there are no further questions, so I'll be ending the session for today. Thank you for joining, and then we'll meet same time, 5 to 7 on next week, next Saturday. Thank you.